Um, Hi everyone. Good morning. My name is Ian Stillwell. I'm a principal geological engineer with BGC's rock mechanics team based here in Kamloops. I specialize in the design and operational support for open pits and waste dumps. And I've also been involved with developing and supporting our rock mechanics laboratory in Fredericton. Um, it's my great pleasure to introduce our next speaker, John Danielson. John's a senior geological engineer who's been with BGC since 2009. And he also specializes in rock mechanics and open pit slope design. So to put it mildly, John has a passion for developing and using new tools to push the state of practice forward and make things possible that were previously impossible. John's going to present today the recent improvements to and validation of Galileo. Galileo is our AI-powered structural geology characterization tool. Galileo not only automates the process of interpreting televiewer data, it also can process and collect other useful geotechnical information recorded by the tool. Um, the significant reduction in processing time, coupled with the additional information it collects, marks a significant step forward for the state of practice. Welcome, John.
Thanks very much, Ian. So I'll just share my screen here, get my pointer up. Okay, so yeah, today I'm going to be talking about Galileo. I talked about Galileo at last year's R&D symposium. So I want to give a refresher to those of you who aren't familiar with it. But I want to focus a little bit more on validation of the tool. We're going to talk about validation in a couple ways. One is the validation that's built into training of the model, and the other is manual validation of some of the calculated parameters. So before we talk about Galileo, we have to talk about what televiewer data is. So televiewer data is collected by sending a geophysical probe down a borehole and surveying the borehole walls. And what it gives us an in situ image of the walls of that borehole. And this is an incredibly important data set for understanding the patterns of the joints, shears, faults, and other fabric that cross-cut a borehole. Here's an example on the right. So we see these discontinuities cutting across the borehole. And in a lot of ways, televiewer data has a lot of advantages compared to the other sources of structural geology data. In contrast to core, the other drill hole source of information on structural geology information, televiewer data gives us an in situ image. With core, it's drilled, it's hauled out of the ground. In some cases, parts of the run are hammered out of a lifter case. And sometimes it's put into a back of a truck and driven on bumpy roads back to the core shed. So there's a bit of interpretation in fitting it back together. With televiewer data, everything is sort of as you see it. On the other hand, processing televiewer data is really boring. It takes a long time. For each of the discontinuities, you have to click along the center line as best you can. The software we use makes the best fit orientation. So it takes a long time, and we humans are really not good at manual, boring tasks. It's not what we're meant for. So in spite of the benefits of televiewer data, there's some really critical limitations. And there's a huge amount of logger to logger variation in what features are picked. There's a lot of variation in what features are assigned aperture. Some people assign aperture or thickness to larger features, but everybody has a different idea of what a larger feature is. People classify things as different things. You might call it fault. Some people might call a fault a fault. Some people might call it a rubble zone or a damage zone. And it's just really to get a consistent data set. Another sort of key and under-discussed limitation with televiewer data is it can be quite biased. So here's an example of dozens and dozens of televiewer data drill holes from different orientations. And what we see when we combine the apparent orientation for all those holes is we see that loggers are much more likely to pick data in the 30 to 60 degree apparent dip range. And this is a big problem because we account for some of the bias around the edge. So you're less likely to hit features that are parallel to the drill hole. That makes sense. But when we correct for that, we actually exacerbate the bias against logging flat structures. So sometimes when we look at individual drill holes, you'll see a lot of scatter in that 30 to 60 degree range, and then almost no data in the middle and almost no data around the outside. And what that means is if there are important structures in this middle area, we might be missing them. And then we might also be designing around structures that look like they're there because we are sampling a ton in this little 30 to 60 degree range, but they might actually not be important sets compared to what we can't see. And finally, yeah, processing televiewer data is time consuming, and it's really a boring job. So that's what we were aiming to solve with Galileo. And Galileo uses deep learning based computer vision techniques to identify and characterize these discontinuities automatically. We focused on picking features that are equivalent to discontinuities, so actual breaks in the core. You can see here where there's just one, these are both mechanical, but there's just one natural discontinuity. Here's the equivalent televiewer image. We pick that one natural discontinuity. Where there are a lot of discontinuities, you see a lot of discontinuities in the televiewer data, and Galileo picks each of them. So Galileo picks these and then gets three key characteristics. The first is orientation, and where we have where the manual loggers do excellent work, we typically see a really great match between the manual logging and Galileo. So here, the main concentration is this one, and the manual logging data is in exactly the same spot in the Galileo version. We see a little secondary set here. It's in the same spot in the Galileo version. So that's kind of equivalent to what folks get, although because we focused on bias, we get less donutting. But we also get aperture for every feature automatically and roughness. And I'll talk about these a little bit later. So we've done a ton of work on Galileo in the last year. We've added a lot of functionality, structure classification, survey quality classification, because of course not all televiewer data is really nice and clean. And we're adding a lot of functionality now. But in the interest of time, I'm going to focus on less exciting new functionality and how we validate the tool. So the first type of validation is related to processes that are common to most deep learning based methods. So to prepare to train a deep learning model, you label as many instances as you can of the features you want the model to learn. So in this case, we made a large data set of images where we've labeled each of the features we want the model to find. We take that data set and split it up into training data set and a validation data set. In our case, we use a 90-10 split. And what the model trains with is the 90%, the training data set. And we train the model iteratively. So the model will update a certain proportion of its parameters or weights using that training data set to try to get the best match between its predictions and the ground truths. But after each iteration, we test its performance against the validation data set, which it really can't see. And then we score its performance on the validation data set. So you get kind of an unbiased look at its performance. You keep doing this until performance on the validation data set plateaus. And if you keep training it too long, the performance will start to decrease. And that's because the model will start to memorize the specific features rather than learning rules as to know what to pick and not pick. I'll talk about the metrics on the next couple slides. Finally, there's a further step where we take the trained model after we've picked a good stopping point, and then we'll run it on a totally separate test data set to make sure performance is what we want. We measure performance using a number of different metrics. The main one is called mean average precision. And that's a function of the precision of the model, which is the ratio of true positives to true positives and false positives. And false positives are like a sine wave, a feature showing up or predicted where there is nothing. And the other is recall, and that's the ratio of true positives to true positives and false negatives. False negatives you can think of as missed features. And these two parameters are combined into this mean average precision score. So let's have a look from our actual validation data set and see where our model performs well and where it doesn't. So our model gets an average of over 90% in terms of where features are being picked, and over 80% for the shape and the location. So let's look at this image here. So we see here in the ground truth, the human labeled data set, this feature wasn't picked, but the model picks it. So that counts as a false positive. The reason why the model doesn't get it, and we typically see this with our more marginal features, it's because in some of the training data, we don't log features like that. So the model really closely replicates what we train it to pick, and when we're inconsistent, the model's inconsistent. Here's another example of a somewhat marginal feature where the humans labeled it, but the models didn't. So that's counted as a missed feature. It's kind of funny if this is manually logged, and if I saw someone pick that and I wouldn't have picked it, you can think, that's just another interpretation. But with deep learning, we're very strict about it. If the humans didn't log it, it's counted as a false positive. So yeah, in some ways, this process is much more robust than our training metrics for training people. We don't have a separate blind data set that we're scoring people on as we get them trained up. And we do our best to QA, but partly because we don't have metrics like this, we end up with databases of geotechnical data that are that have inconsistencies and that aren't always reliable in the same way. So recently I had the opportunity to travel to site and compare Galileo results against physical core. And one of the parameters we looked at here was roughness. So I mentioned before that we can get estimates of roughness from Galileo. And we do that by finding the center line of each identified discontinuity. We subtract the best fit orientation, and we're left with a roughness profile. And we score roughness as the average deviation from that center plane. You can see that here, this looks smoother than the one below, which is stepped. You can see that step in the roughness profile. But we weren't sure how tool resolution would play out, whether estimating roughness around the circumference was valid. So what we did is on site, we took a number of 14 3D scans from core. We matched them up with where Galileo was picking those features. And we were able to directly compare the roughness from Galileo with the roughness from the core. And we looked at the roughness of core in two ways. One is we took the full area roughness, which is an assay parameter, and we also measured it around the circumference, which is kind of more similar to how Galileo does it. And what we see is looking at the circumference roughness versus the Galileo roughness, you get a nice increasing relationship, but it's kind of offset. And this kind of highlights how resolution plays into things. So at this site, the teleview resolution is 6 millimeters. This is relatively coarse and coarser than we often work with. Most of our training data is 3 millimeters. And you can imagine if you look at Mr. Smiley here, even if in reality his smiley was perfectly smooth, because it's pixelated, what it ends up adding is half of the resolution in roughness. So it looks like there are little rough drags here, even if his smiley was perfectly smooth. And that's what we see looking at our comparison. If we shift it by half a pixel resolution, we see that increasing relationship, but now it's showing up on the one-to-one line. Interestingly, looking at just the core scan roughness in terms of area against the circumference roughness, even that relationship is pretty scattered. And it's pretty interesting that at the smooth end, what we see is a really tight relationship between circumference roughness and area roughness. But as you get rougher, the variability gets higher and higher. If you think about it, this makes sense because the rougher it is, the inherently more variable the surface is, and you're more likely to get skewed by local changes. So I think I better hop to the conclusions. In essence, looking at the time here. So I just want to leave you with these two thoughts. So in some ways, deep learning models are black boxes, but in other ways, I think they're much more transparent than what we do as humans and how we train humans. In terms of performance scoring, they're much cleaner. And then the other thought is looking at the Galileo results side by side with physical core was really instructive. It highlighted the differences from using the coarser resolution data at this site and provided support for our roughness estimation method, but also really valuable insights on how we can use that data and some of the limitations related to the resolution. So what we're doing as a result of this site visit, we're adding more of this coarser resolution data to our training data set. And we're recommending that the client, if they can, move to finer resolution data.